It is 3:30. Welcome to Statistical Computing for Scientists and Engineers. That's a new class at Notre Dame. I am new here as well. You know, this is my first year. Well, I'm sorry. This is the first year of teaching at Notre Dame. All right, so it's my second year here. You may wonder about the title of the course. It could have been things such as machine learning. You know, I did not want to use that for political reasons. It could have been Bayesian inference. Half of the students from engineering most probably would not have liked the title. So I wanted something neutral, and statistical computing sort of fits in that category. As you know, the lectures will be taped, and so we're going to learn how this thing is going to work on our way. But keep in mind, when you ask questions, I'm going to have to repeat them because the microphone will not pick up anything you say. Okay? So there's no need to speak loudly or anything like that. I will have to repeat your question. Okay. There is a website, in case you have not noticed. It is on zabaras.com, statistical computing. And all the information regarding the course is going to be given there shortly after the lectures. Okay? The website is sort of is a placeholder for everything for you and for me as well. Okay? So you will find the videos, hopefully, the lectures, references, homeworks, response to questions you may have, etc., etc. There are 2 lectures every week, Monday and Wednesday, 3:30 to 4:15, and we have planned for recitation and office hours for the TA on Fridays, 3:30 to 4:15. However, I'm going to use the Friday's time for lectures so I can predict, you know, since we do predictive modeling here, right, Bayesian inference, I can predict all my travels ahead. So we're going to use some of the early Fridays for lectures, and that includes this Friday and next Friday. One promise, there will not be any extra lecture period during the semester. It will be maybe less than what we're supposed to offer, but certainly not more. Okay, but this Friday we're going to have a lecture, and so I hope you come. The TA, and it is a completely volunteer TA, is Zize Zhang from Civil Engineering. Some of you may know him. He has taken a lot of courses in related topics, both at Notre Dame and also at Carnegie Mellon. Unfortunately, he is not going to be with us until the first week of September because he is on an internship overseas. Okay? So that means that the first homework may take some time to come. All right? And you will not be able to get much assistance from him until he comes back. So we talk about the website. There will be no exams in this class, simply because it doesn't make sense. It is a heavy computationally oriented course. Having an exam asking you trivial questions, it just doesn't help. So we're going to have 60% of the grades going to homework, and there's going to be a final project will be 40% of the grade. The homeworks, all of them will have a significant computational component, and you may find the course to be a little bit intensive when it comes to the time you have to spend working on the course. So the assumption here is that you are in this room because you value the role of Bayesian inference and statistical computing to your research. So I'm going to try to educate you as much as I can in one semester so you can do things that are useful in your research projects. But if you're here just for another course, this is not the right course to be. Okay? I want everybody who's here to be here because they want to learn, which means you are going to have to work hard. Okay? So I cannot. Now, you're not going to have to work hard because I'm going to give you too much work. Simply to be able to follow, you know, for every hour of lectures, you're going to have to put 5 or 10 hours of reading around to figure out what is going on. Okay? We cannot make the course an elementary course because simply you're not going to cover anything that's of any useful there will not be any useful information there. And so we may have 1 or 2 introductory lectures, and after that we will try to pick things up and do things relevant to statistical computing. The final project from past offerings of similar courses in other universities, I can tell you, is where about half of the learning happens. So the anticipation would be that these are not projects you submit to me and you get a grade, but these are projects you share with the class. So we're going to have sort of a workshop at the end of the semester where everybody will present for, half an hour, if that's what it takes, your project. And there will be a lot of learning because, we're 45 students in this class. So you can think if everybody, let's say, works on his own or her own, we have 45 projects, 45 different topics, and lots of learning there. Okay, so if we miss some topics that are of value to you, I am almost certain will be covered at the end of the semester. And all information, software, reports, videos for the final projects would be posted as well on the website. So we're going to do it like a conference, sort of. Okay, so because I take this as a very serious part of the course. Okay. There are not really needed books because the notes will contain a lot of information and you will be already tired reading the notes. But if you're in this area for the right reasons, you need to own a lot of books, okay? Because there are books you will have to visit very often. So I don't list them in any particular order, but certainly the first 2 books in machine learning are standard textbooks. I would not hesitate to say go and buy these books because you will need them if you really appreciate this area of research. The first book is a much better reading than the second. The second, it reads like an encyclopedia, but only the references that it provides, it makes it a fantastic book to own. Okay. The third book, it's maybe a 15, 20 years old book, but the standard textbook on Monte Carlo methods for scientific computing. Okay, it's about 300 pages, and I believe when I was trying to find the link here, there is a free electronic version at the Notre Dame library. So you can basically download the whole PDF for free. Okay. The book by Roberts, I don't know if there is an electronic version here. They used to be in one of my former universities before, but I think I couldn't find one here. It's also on Monte Carlo methods. It's way more modern than the book by Liu. And the nice thing is it comes with video lectures, video presentations. So there is a lot of content that goes with this book that you can find online. So, again, if you are going to be using Monte Carlo methods for your research, this is a very nice textbook to use. And you notice below there is another book by Roberts. Actually, there is a sequence of maybe 5 books that he has written. He writes one book every year approximately on different subjects. And there is a third book that I am going to use, and I'm going to assign some homework, that's called the Bayesian Core. And some of these books are available online. There are e-books basically, but I'm not sure if the library has them. Okay, so you may want to check those. A fantastic book for probability theory with a very new perspective is the book by Janes, Probability Theory, the Logic of Science, and it's available for free on the web, in his website. So if you have not polluted your probability knowledge with different instructors and different textbooks, etc., his thinking is sort of very universal. It goes beyond mathematics and statistics. It brings everything in nature together. That's why he basically claims, as you can see from the title, that probability theory is the logic of science. And it doesn't matter what science you refer to. Okay? So this book was put together by his students because when he wrote this book, his colleagues thought it was too provocative. so they would not even accept to publish any of his papers, but now it's sort of a standard textbook in this area. There are a few more books on the website, so you can visit those, and of course I will be giving you more as we do specific things. Okay, course objectives. To introduce statistical methods for stochastic simulation of complex physical systems in the context of Bayesian analysis. So all the statistics we will do will be Bayesian statistics. If you don't know, obviously when you say Bayesian statistics means there must be another type of statistics. If you don't know anything about the other side of statistics, we don't really care, and I wouldn't tell you, because everything we will do is Bayesian, and that's the only statistics I know. Okay? We are going to introduce, maybe a third on the way, approximation methods that will be useful to make Bayesian analysis realistic, and those will include ideas from Monte Carlo calculations, and also approximate inference techniques, a little bit of more modern way. They don't substitute really each other. There are two alternative techniques that do well on certain problems, they don't do well on other problems. At the end of the day, you will find out at the end of the class that if nothing works, Monte Carlo methods always work. Which means you have to be very good in Monte Carlo methods, and unfortunately, you don't see much emphasis in machine learning books. They usually devote a chapter, because most of the examples they discuss, they are not really high-dimensional, very complicated physical systems, so they don't really need the machinery that comes with Monte Carlo to that level. But we will review lots of these ideas in this course. I really, this is a class that has 45 students from 10 departments, okay? So, and it's fantastic that we have students from engineering, physics, chemistry, biology, math, statistics, computer science. I don't think you will find many classes like that at Notre Dame or any other university, okay? So the idea is I respect the fact that you come from different disciplines, and I'm not going to try to speak as an engineer or as a computer scientist. I'm going to try to give you the essence of what Bayesian analysis is, and the way you can potentially apply it to whatever problem is of interest to you. Okay? So don't, I am going to try to use the universal language of mathematics basically to communicate with you. Which means we're going to sort of adjust, and so don't start asking me within the next 5 minutes, are you going to do any examples of this? I remember recently, this past June, I was giving a short course in another country, and I was asked basically from within 5 minutes, can you do some examples? I had not discussed what the whole course was going to be, and they were asking me, can you do some examples? Well, I can, but we first need to learn what this course is about. And for that reason, by the way, I am not going to show you applications of statistical computing today. I am going to wait until we have learned the basics, and before we discuss algorithms for particular problems, then I will show you applications. So you have to trust me that obviously you're in this room because you know this is a very important area, right? We want to believe that. Okay, so obviously we're interested to propagate uncertainties within a Bayesian context. Everything we do is going to be driven by data, and the data can be experimental data, can be simulation data. And we're interested to do predictions, all right? In essence, we need to know things we cannot measure, all right? And we need to do these predictions with quantification of uncertainties, and these ideas of Monte Carlo and variational methods, these approximate inference methods will help us to do that. Now, these algorithms that you will see here, a lot of them sort of existed long ago in, let's say, in statistical physics, in statistical mechanics. For example, all the ideas of approximate inference were known back in the 60s in statistical mechanics, and people in machine learning picked them up way later. And some very distinguished machine learning researchers, you will see they're basically physicists, or they used to be physicists. So there is always something to learn if you come with a different perspective on these topics, and hopefully we will, your knowledge in different areas will help us to do this course a little bit better. Okay. Now, I don't have to tell you why this course is relevant to science and engineering. The applications basically go from physics and chemistry to genetics, all areas of machine learning. Because we're interested on a Bayesian setting, we're going to basically explore this concept of prior information, prior beliefs, and in the analysis, which is basically what makes a statistical model a Bayesian model. All right, so we're going to spend maybe 1 or 2 lectures to discuss how this prior knowledge comes in our computational algorithms. Now, for those who have taken other courses, this idea of prior modeling is, or it used to be a reason why people don't like Bayesian thinking. They say, well, if you have to introduce some prior knowledge to make this to work, your prior knowledge is different from mine, so your garbage is different from my garbage. That argument, I think, was lost a long way ago, and you will see that there is a principal mathematical formalism to introduce this prior knowledge that removes sort of all this ambiguity in the philosophical discussions here. We're interested on problems that are sort of challenging, very high dimensional problems that you cannot visualize. All right, so you do solve problems in X, Y, and Z. We would like to be able to solve problems where maybe we have 1,000 or 10,000 variables, and we would like to know how the solution looks in 10,000 dimensions. And so you need sort of to allow yourselves to think big, all right? And big not in the context of big data, because the word big data is always under debate, what big data means. I mean, if I go in the room, some of you who work in big data, maybe if we discuss it, your big data is not as big as you think. Or it means different things to different people. Certainly, we want problems that this complexity of high dimensionality, this scarce of dimensionality, it is a difficult problem that we need to address. So Bayesian statistics, let me go back, is, I will say, one of the hottest topics because it has revolutionized everything, but also has changed the way we teach statistics, we teach modeling, computational modeling. Actually, I can tell you it's almost a standard topic now. If you write a computational science proposal, unless you discuss some statistical aspects, some uncertainty modeling, basically your proposal will not go anywhere. Nobody cares about the old world where you put some input, you get some output. Now the idea is, well, how confident are you that your output is correct when your model is wrong? Because all models are wrong. So how do we quantify that? So scientific computation and scientific computing are basically an integral part with Bayesian statistics, and it will come up in our discussions. Now, classical problems in modeling, let's say optimization, you can actually pose them as statistical inference problems. And if we are lucky, one of the homework problems I'm going to give you is to solve a linear system of equations, AX equal to B, using sampling methods. All right, so something that you think is weird, A is given, B is given, and I'm asking you to solve AX equal B using statistical methods. But you will see that there are lots of benefits in certain classes of problems to revisit a lot of the things you learned in computational linear algebra and optimization theory. Okay, there may be more efficient algorithms that introduce some statistics in your problem. So let's see, the topics and the list. I don't promise that I will cover all of this, all right? It depends how rapidly you can progress on your own readings, but hopefully we will have some background on probability statistics and information theory, maybe the first 2 lectures. Maybe 2 lectures or so on the fundamentals of Bayesian statistics. I am going to give you some Bayesian algorithms for doing, in a modern way, your standard tasks of regression, classification, model reduction, supervised and unsupervised learning. And at that point, I will emphasize why we need sampling methods. So a lot of, for example, when you do Bayesian analysis, if you think of doing predictions, that involves a very high dimensional integral, and we will see that. So textbooks usually leave the integral there, and usually that integral exists in some analytical form. Let's say it's a Gaussian, and everybody tells you, so we know how to sample with a Gaussian, no problem. But in all other cases, that integral has to be calculated numerically, and the only way you can do it is with Monte Carlo methods. Since we're going to do Monte Carlo methods, a nice application will be to do dynamical systems. So you will hear, to some extent, applications to time series models, hidden Markov models, topics that are relevant basically to many, many disciplines because dynamical systems are universal. Okay? So I will give you some interesting homeworks when we reach that area. We're also going to do state space models. We will complement Monte Carlo methods with variational, these approximate inference methods. Maybe 1 or 2 lectures on exploring sparsity in Bayesian models. And since I mentioned something about model error, for every task there are multiple models. Which one is the best? Right? So that the only way you can actually address this, in a rigorous fashion is the Bayesian way. And this can imply many different things, right? So, it can be models that a discrete versus a continuum model, or it can be a model with this sort of basis functions versus a model with some other basis functions. Or it can be a model where you throw 10,000 basis functions and you want the algorithm to select for you which ones to keep. All right, so we will see how this can take place within a Bayesian paradigm. I want to cover mixed models because they're essential for many tasks, and that requires that we learn something about expectation maximization. That's sort of one of the top algorithms in statistics. And I do hope if there is room to discuss some non-parametric methods for doing supervised and unsupervised learning. And then there that says other, that's where all your projects come, and there will be another 45 projects and 45 different ideas that you guys can educate the class. All right, any questions regarding how the course is going to proceed or anything else? I like interactions, so even though we're taped and your voices may not come at all, I need to take breaks once in a while, which means you have to speak. All right, thanks for speaking. So we are proceeding with some trivial introductions. We need to take advantage of the time, right, where there's way too many things to cover. The class is very diverse, so it's very difficult for me to assume that everybody knows everything. So I need to give you as much as I can. I don't promise I will cover all the slides in these lectures. So if I post something and it has 50 extra slides, you have to read them. Okay, maybe there are proofs, maybe there are examples there. But we will not be able to cover everything in the lectures. Now, when I say introduction to probability and statistics, that may imply the equivalent of maybe 2 or 3 graduate courses, okay, even at the elementary level. And that means that even on these elementary slides, I may be jumping from one topic to another, trying to give you buzzwords that we will hear later on in this course. So don't get sort of, if you don't understand something, don't panic, because these concepts will come up again and again and again, right? So I'm going to be throwing things that sort of look like to be out of sequence. Okay. Before I mentioned to you, we're not going to do anything but Bayesian statistics, but here let me just mention the classical way of probability has to do with the long-run frequencies of events, right? How many days a year is going to rain? Well, we're not interested in those type of things, because the type of things we want to model uncertainties, we cannot really repeat the experiment that way, okay? So the concept of probability that we're interested is basically a concept that has to do with our belief for something to be true or not, okay? And that belief can be based, you know, maybe it does come from some experience that has to do with some frequencies, if that event is populated, but, you know, it may have to do with something very personal to each of us, okay? So we want to quantify uncertainties, but usually it's not related with frequencies of an experiment. For example, you know, and this is a real problem, if you're trying to model the probability that the polar ice cap will melt by 2030 or 2040 or 2017, it's not like you're going to be committing 25 experiments to do that, right? So this is not something that is going to be repeated, okay? So this is the type of statistics we're interested in. The good news are the rules of probability, all the mathematics that go with it, they're identical both for this frequentist paradigm and the Bayesian paradigm. So if you know one, all the mathematics transfer to the other approach, but of course the interpretation of things will be very much different. So everything you will hear from now on will be on Bayesian probability. So I am going to start clicking slides very rapidly, only mentioning some keywords as we see, and the rest you guys can read on your own. So we're going to model random events, right? So I'm going to start with the definition of what I call the sample space, all right? So this is the space of all possible events. So if you roll a dice and it has 6 sides, right, your sample space would be 1, 2, 3, 4, 5, 6. And an event will be a subset of that sample space. The ideas from set theory that you have seen in high school, they carry on basically to this event. So, you know, if you talk about the union of events, this is exactly the same thing you learned in set theory. Or if you want to talk about the intersection of different events, or if you want to talk about events that they are mutually exclusive, or something that is the empty set, those hopefully are concepts that are familiar to you, but they will come up in the type of calculations we do, all right? So this is, you can read, these are very elementary slides, so you can look over, and you know, you can visit us if you have any questions. Now, the laws of probability basically, and this is amazing, they're what you see on that slide. I mean, probability theory has 2 or 3 or 4 axioms, and that's it. And we will see on another slide there are 2 fundamental laws of probability theory. But what is amazing is with simplicity you can get things that are very complicated. You don't need to start with a very complicated theory to solve complicated problems. Simple theory is sufficient to, you know, to address even very complicated problems. So what are the fundamental laws? The probability of an event E. So E is you know, a set from the sample space. It's between 0 and 1. The probability of the whole sample space is 1. The probability of the null set is 0. And for any sequence of events that they are mutually exclusive, the following holds. The probability of the union is the sum of the probabilities of these events. There are some mathematical issues here if the infinity holds or not, but they're really not relevant to our discussion. I'm going to bypass this. All right, so let me give you a few examples. So let's discuss about a discrete, a finite size sample space that I denote here as this calligraphic X. And I am going to, in this space, right, let's say this is my dice that can take values 1, 2, 3, 4, 5, 6. So I am interested, if I do an experiment, if this event X will come to be 1 or 2 or 3. So basically, the probability that I affiliate is between 0 to 1 to each of these events. If I take all possible outcomes inside this sample space and I sum all the probabilities, I get 1, right? And so let me give you a visual example. Here is a space that contains only 4 elements, and I assign equal probability to each of them. So this variable X can take the values 1, 2, 3, 4. So the probability I assign is 1/4. And here is another case where the space is the same, but I only assign the probability of 1 at X equal to 1. And the notation here will be useful in this course. This is the indicator function. So this is non-zero when X equal to 1. It's like a delta function that when you integrate it will get you 1. All right, so let me talk about joint probabilities, and then I will give you the 2 fundamental laws of probability theory. So let's say that we talk about 2 events X and Y, and they're discrete. So for example, here is a grid that shows the values that X can take. So there are 5 values. These are the values that Y can take. And I'm interested to define what is called the joint probability of X and Y. Okay? So if I repeat, let's say, an experiment, I told you we're going to be Bayesian, but just to start with, and I repeat this experiment n times, I am observing how many times I am going to get my X to be Xi and my Y to be Yj, and let's say the time is Nij. So this is how I define the joint probability distribution for discrete events X and Y. So in this little plot here, Ci is the times out of these n experiments that the variable X will take the value Xi. And Rj is the times the variable Y will take the value Yj. Okay, so remember those, and I'm going to show you this plot again. So let me do something, let me show you the 2 most fundamental laws of probability theory. And I know you're not going to believe me yet, but very complicated expressions later on will only be derived from these 2 laws. That we will discuss them shortly. Everything in probability theory is really an outcome of those 2 equations. Okay? And of course, it will be up to you to use these 2 equations in an intelligent manner as you try to do calculations. So let's see what these 2 equations are. Can you look at this equation on the first one and tell me what exactly are we doing? This is the sum rule. So what do we do in that equation? So remember we talk about the probability of X and Y, the joint probability of 2 events. So what do we do on the first equation? On our simple, setup that we had here, but it can be general. So what exactly are we doing? I notice on the left-hand side from the probability of X and XY, suddenly I only have here the probability of X taking the value Xi. So what happened to Y? We marginalize it, right? We integrate it out. So effectively, the sum rule says that I can get rid some of the variables in a joint distribution by summing over all possible values that they can take. So, y can take all these values that you see on this axis. All right. So if we sum, we can go from a joint distribution to the distribution of the single variable x. Okay. So this is the sum rule, and I'm going to give you this also in an integral form, so you can see how it will be applied to continuous variables. So let's do the product rule now. And before we see the derivation, because really this is the derivation for the discrete case, let's see how this product rule looks like. It says that the probability of x taking the value xi and y taking the value yj is the probability of y taking the value yj, given that x has taken the value xi, times the probability of x taking the value little xi. So here we introduce what is called a conditional probability. So we are now looking at the probability on one event, considering that some other event has happened. Okay? Now, how is this equation comes and what does it actually mean? The derivation is very simple. You remember we defined this joint probability distribution as nij divided by n. So if I plug in the ci on the denominator and numerator, I have this fraction here and this. So let's see, what is nij divided by ci? What was ci again? It was in the n times, how many times? The variable x, x took the value xi. So what is nij divided by ci? Is considering that x equal to xi has happened, is how often yj will be observed. So the space that I'm looking now is not n, right? But is how many times x equal to xi has happened, and that time is ci. And similarly, ci over n is basically the marginal probability of x taking the value xi is how many times out of the n cases I'm going to get the variable x to be xi. So look very well at these two equations, because in this course you will see them in various forms about 1 million times. And if you ask, are there any other laws of probability theory? The answer is no. That's it. We're done basically. And the rest is a lot of mathematics effectively and manipulating things, but they have to obey this type of equations. Okay? So the sum rule has to do with marginalization, and the product rule basically has to do with this introduction of the conditional probabilities. And I am giving you here an example of the chain rule, where if I have d variables, and I denote here all these variables x1 to xd with this notation, you can write this exactly as a product of marginal distributions, okay? P of x1, P of x2 given x1, etc. And you can do this in any sequence of the variables. We will see this again later on in the course. So, sum rule and product rule for continuous variables. The marginalization that you see on the top is now comes in the picture as an integral, and the product rule comes here in this fashion. Now, there is an ambiguity here because I have not defined, density functions for continuous variables. So treat this as probabilities, okay? And we will, but you can guess, for those who have seen this before, we will be able to do exactly the same equation for densities once we introduce those. All right. Now, I told you will see these equations thousands of times. So look at the equation on the top, because this is basically a combination of both the sum and the product rule. Okay? And it is in many ways also Bayes' rule. All right? And it is the most fundamental equation for this class. So what do I do to go from here to there? Which rule am I applying? This is product rule, all right? What do I do in the numerator? Again, the product rule. And what do I do in the denominator? Sum rule and product rule together. All right? So basically, P of y requires marginalization of x. X can take multiple values, and I use for each of those values the product rule, and then I sum up. Okay? So this thing on the denominator, it will be a calculation that is going to give us most of the headaches, because it requires, if this, for example, you had many variables, means you have to integrate them out, and that integral may be very high dimensional and very complicated to do. And so unfortunately, we will have to deal with this, and it's going to be a difficult part in the various algorithms. Okay, we have, I'm surprised how fast time goes, because I was planning to cover today 85 slides. Okay, but reality hits, it's all probabilistic. Okay, so let me do one example of the application of this product and sum rule. This is from Chris Bishop's book. So let's say that you have two boxes. One, a red box, and one is a blue box. And the probability of selecting one of the two boxes, just maybe you like blue color more, so you will select with higher probability the blue box. Let's say 610, and the red box 410. This is what we call sort of the prior probabilities. Now inside the boxes we have apples and oranges. Okay, so here's the problem that is posed. If you select an orange, what is the probability that you selected that orange from the red box? I repeat again, all right? So if you selected, F stands for, let's say, fruit. If you selected an orange, there are oranges here, there's orange there. What's the probability that you selected it from the red box? So let me just put the equations up, because we don't have lots of time. Actually, I'm going to start from the bottom equation. So really what we want to calculate is, if we selected an orange, what's the probability that we selected the box was the red box? And you can see here the Bayes rule in action on the numerator that I had before. And the denominator, you remember, it involved terms like this, where I also sum from the red box and the blue box. Okay? So effectively, to calculate this probability, I am going to have to calculate, let's say, these two probabilities on the top, right? So let's see, what's the probability that I will select an orange if I pick up to do this from the red box? The answer is very simple. I have 1, 2, 3, 4, 5, 6 oranges out of 8 fruits, so that probability is 6 over 8. And this is our prior probability, which is 4 over 10. And if you do the calculation for the denominator, you get this 9 over 20. Please do the algebra, check it up. And then you can see that the probability now that the box is the red box comes out to be 2/3, which is much higher than 1/2. It's much higher than the prior probability. In other ways, you know what? Because there are lots of oranges on the first box, if you select an orange, there is more chances that you selected it from the red box. And let me do one problem, and we will finish there. This is sort of a historical example that goes many, many years. So I'm going to put everything up, okay? You may have seen this before. So you come from a trip, let's say, in the Far East. You go vaccinated, but still you come with a disease back, okay? And so let's call this disease tuberculosis. and we know that 0.4% of the population has tuberculosis. So this is the prior knowledge we have that usually comes from some population average, all right? So the prior that you will have tuberculosis is 0.004. Now, you come and you go to be tested because you don't feel good, and you know that if you have the disease, the test will be positive 80% of the time. Now, if you don't have the disease, the test still will come to be positive 10% of the time. That's what we call false positive. So the question is, if the test comes positive, should you start panicking? And obviously, the common sense answer would be, oh, you know what? 80% of the time the test comes positive. If you have the tuberculosis, then you know you are ruined. But actually, if you use this product and sum rules exactly the same fashion that we presented before, and you do the calculation, it comes out that if the test is positive, the probability that you're sick is actually 0.031. Okay? And the reason the calculation gave you such a low probability, you know what it is including the prior information that otherwise you will omit. So you remember that a very small percent of the population has the disease. I forgot what the number was point something percent, yeah. So that is what makes the difference. Okay, so when you have prior information, you need to use it. Okay, I know they will cut us off in 1 second, so thanks for coming. There will be a lecture this this Friday. We will post the videos, we will post the lecture for today, and you can read the rest of the slides that I will omit, and we will continue on Friday. I have 30 more minutes? Amazing. In normal circumstances, you will say that was out of excitement, that I don't have to teach, right? All right. Now, why did I think, 4:15, 4:45? That's amazing. Okay, all right. All right, guys, come on. Now we can do lots of stuff. Any questions? Any questions with what we did with this example? No? Okay, it's trivial. All right. So let me use exactly the same product and sum rules, okay, for a problem from machine learning. And those from computer science, I want them to look on the equation on the top and tell me what it implies. Don't read. I don't know if I can remove. Okay, I cannot remove the rest. Look at the equation on the top. So I have data X, okay. Obviously, I am trying to group them to different classes, right? And so this probability on the left side, it tells me if I have this data point X, it tells me what's the probability that it will belong to the cluster C. So give me an idea of what are all the factors that are involved in that calculation on the top. So what is this probability? P of X given that Y equal to C. What is that probability? Remember, I give you lots of data. I'm not telling you how you're going to train the system, but somehow you want to group the data to different clusters. And one of those clusters, I call it C. So C can be 1, 2, 3. All right? So what is this term tells me? What is that term, just with words? Is the probability of what? So it gives you the probability of X if it belongs to cluster C. So if you think that each cluster is another Gaussian, for example, right, and you have a mixture of Gaussians, it says if you're in the Gaussian C, what's the probability of X? Okay? So, and in some sense, we call this a generative classifier because it requires that for each cluster you have a model for how the data are generated. Okay? So, obviously, this is a prior, if you like, on the probability of having a cluster, the probability of having a cluster C. And on the denominator, we had that marginalization that we saw before, where we sum for all possible clusters C prime that X can belong to. Okay? So this calculation, would be sort of the standard calculation that we will do when we start discussing about classification. And again, it's an indication that this sum and product rule are the rules that govern most of the probability theory. All right, so let's make things a little bit more interesting. We're going to define two events to be independent when any of these two relations that you see there is valid. So here, I define the dependence when the probability of A happening and B happening is equal to the probability of A times the probability of B. A much better way, an equivalent way to define this is in terms of the conditional probability of A given B, all right? And let me just go to the next slide, to the next question. You notice if you manipulate, this is Bayes' rule basically, this is what I had even on the previous equation for classification, it's the same equation. But if you combine this equation and the second equation together, you see that the conditional of A given B, if A and B are independent, is equal to P of A. In other ways, if A and B are independent, knowing B makes no difference on what I think about A. Okay? Now, why is this concept of independence important? Because you will find out in this course that many problems can only be solved by exploring these independent relations. If everything depends on everything else, good luck. Mission impossible. If you can identify these independencies, then you can have very efficient algorithms. And I will give you, I think, I have an example basically with calculations of variables that you may need to describe if you don't have independence. So before I do that, let me define also the conditional independence. So if you condition on an event Z, you can still talk about X and Y being independent given Z, and it is the same equation that we had before. The only difference is you condition everywhere with Z. A lot of times when the equations get very complicated, when you have conditioning, right, keep carrying given Z as if it is not there, right? So this equation, when you look at it without the Z there, it says P of X and Y, it's P of X times P of Y. All right, but of course here we're interested given Z. So this is conditional independence versus the marginal independence that we discussed before. All right, this is something that you need to keep in mind when we discuss many variables together. If you have pairwise independence of, let's say, 4 variables, that doesn't imply that those 4 variables are independent together. And I have a simple example. I don't know if it is the best example, but let's discuss it. So we have, let's say, 4 balls that we number them 1, 2, 3, 4 in a box, and we draw at random balls from this box. We assume that the probability of getting 1 or 2 or 3 or 4 is basically they are equal, 1/4, and we define 3 events. So x1, ball, the event x1 is that ball is 1 or 2. x2 is that I am drawing 2 or 3, and x3 is that I'm drawing 1 or 3. Can you look at this calculation and tell me if this is true? Basically what I'm claiming here is that x1 is independent marginally of x2, and similarly x1 is independent of x3, etc. Why is that the case? What's the probability of x1 and x2 together? look at x1 and x2, says it's either ball 1 that I'm drawing or 2, and x2 is 2 or 3. So x1 and x2 together, what is the event? The event is that I'm drawing 2. And what's the probability of 2? 1/4. And if you take p of x1 and p of x2, each of those events is 1/2 times 1/2, so 1/4. So you can see that this is true. But look at this event. If you take the probability of x1 and x2 and x3, is 0. Right? You know, this is 1 and 2. Okay, they have 2 together, but when you go to event x3, there is no 2. So this is 0, but the probability of this product of the marginals is 1/8. So effectively, don't check if you have many variables if they are independent in small groups, because you are interested to check independence on all the variables together. And actually, that's an open, very difficult problem in high dimensions. It comes a lot in defining the structure of graphs, probabilistic graphs, and other things that we will cover maybe in another course in the spring, but it is not a trivial topic. So let me do an example, and here is where I sort of, I am starting bringing notation that you will see way down the road, possibly even in another course. But let's consider the following. I consider 3 events, all right? And the zeros, the way I have them here, will be sort of a graphical way to indicate what depends on what, okay? So the idea here is A depends on C, B depends on C, and this marked element C implies that I already have observed C. So what is C? C is the fact that it's raining today. Surprisingly, it's not raining in Notre Dame today, right? But let's say it's raining today. A is it will rain tomorrow. Obviously, you can see that A depends on C, right? If it rains today, there is a high chance it will rain tomorrow, okay? Similarly, B is the ground is wet today, right? So that depends. If it rains, obviously it will be wet. Now, we will learn in, graphically to figure out independence relations. But here what I'm claiming is that given C, and that's why it's marked, that A and B are independent. So effectively, I can write this with this nice equation here. So given C, all right, so C is fixed on both sides. If I find the probability of A given also B, then B doesn't enter, it doesn't bring any new information once I know C regarding A. So I don't need to know that the ground is wet to change my mind as to what happens to if it will rain tomorrow or not, because I know it rains today, and that's good enough to make this probabilistic assumption of independence that you see here. Okay? So the notation, by the way, of independence is sort of like the orthogonality relation you use with vectors, that A is orthogonal to B given C, but it's really not orthogonality, it is independence of events. Okay, so I told you that I'll say something about why independence is so essential. Okay, so let's see this example. We have 2 variables, x and y. So x, let's say, takes 5 values. Y takes 6 values. So to describe this joint probability of x and y, I need 29 entries to this table. Why 29, not 30? Because when I sum all the events, right, I should get 1. Okay? So remember, we need 29. Now let's say that x and y were independent. How many values do I need to describe p of x? 5. Why 5, not 6? Again, because all the events for x have to sum to 1, and y similarly it is 4. So instead of 29, do you prefer 5 plus 4? So think now, if this was not 29 but was 1,000,009 versus, let's say, 10,000 or even less. Obviously, independence relations are very essential to reduce the computational cost. And of course, the difficult task is how do you come up with this? What depends on what? And that obviously requires a lot of training. I am not going to go in the next 6 slides, but I want you to read them, or 5 slides. They give you sort of functional relations of variables that they are independent or conditionally independent. Okay? So just to get you a sense of what the slides are about, if x is independent of y given z, then the joint probability of x and y given z can only be written as a product of a function of x and z times a function of y and z. So you can separate basically x and y in the product of two functions. And this is what you actually take advantage when you build algorithms, that the only way for this probability to imply this independence relation is to have a functional form like that. The derivations are literally trivial, so I am not going to discuss them, but I want you to read them, so I'm going to leave the slides with you, and I have a number of similar examples that you can train yourselves on checking independence relations. All right, so let's talk about random variables, and in particular continuum random variables. So let's start with a real value random variable x, which is a map from the sample space of events to the real line R. So random variables are functions. You give an event and you get a value in real line. Okay? So in generic notation, the event, we call it little omega, that belongs in the sample space, and it gives you a real value little x. And the random variable we denote as capital X. Now in many books, and maybe even on my slides, by not paying attention, sometimes we don't bother with the little x and capital X, but it's a good idea to use little letters for realizations, capital letters basically for random variables. Okay? Now, if somebody gives you, let's say, a subset of the real line R, and I call it this B, so let's say B is an interval from 0.3 to 0.7, and you ask, what's the probability in that interval from 0.3 to 0.7? Well, what you need to do is you need to compute the probability of all the events that map x of omega to that region B. That's how we define probability basically for continuous variables. There are different events that that are mapped in that domain of the real line B. So the probability of those events omega will give us this probability defined over B. And that's where this concept of probability density comes. So this is the probability we discussed here. Okay? And the density basically comes in a way that the integral over the domain B gives you that probability. So you can think of this being the derivative of this probability function, capital of P, or that capital of P is the integral of the density of the random variable capital X. A lot of times, the notation, depending on what literature you read, they simply write P of X. Lots of times, if you have many random variables, you may want to indicate capital X, and it can get confusion, a lot of confusion here. If you have many random variables and you start with one distribution, then you integrate many variables out, right? So at the end of the day, you need to know what variables are you're referring to when it comes to the probability space. So here is a little bit of a graphical representation of what we define as the cumulative density function. So if you take your density P of X and you integrate it from minus infinity to Z, okay, this is the definition of the cumulative density function. If you integrate it from A to B, Basically, in the real line, this will give you the probability in being in the domain from A to B, and it is basically the cumulative density function at B minus the function f at A. I'm going to put all the standard definitions that you have seen in undergraduate course in probability theory. The mean of your random variable is this nice formulation here. This is the variance. It requires that you compute the second, what we call the second moment of x. The standard deviation is the square root. You can define actually this for any function of your random variable x. So if you have any function of x, you can, similarly as before, instead of having x here, you can plug in the function t of x, and similarly in the variance. And you can go to higher moments. In particularly, we may use here and there in the course the third and the fourth moment to figure out how far away, let's say, from a Gaussian a distribution is, and this skewness and kurtosis are good measures to allow us to say something about that. Okay. For continuous case, of course, you substitute summations with integrals. And I'm going to come back to this on Friday on these conditional expectations because this is very important, but let me just define. If you have a function and you want to find the expectation, but for a given y, then the probability that you average with has to be the conditional probability of x given y. All right? So when you try to find expectations given y, the only thing you have to substitute is, instead of p of x, use p of x given y. There are some nice formulas that we will revisit in a follow-up lecture. Let me just give you an example of something that, it seems to be not common sense, but it is something that often comes in practice. The expectation of a random variable is not necessarily the value that we should expect the realization to have. Right? So in other ways, the expectation is not a value that the random variable takes. Okay? So and here is a simple example. Suppose your sample space from -1 to 1, and the distribution is uniform, which means the probability is basically 1/2, right? The space is 2, so the probability of being having any event I, any subset from -1 to 1, is really the length of that event divided by 2, because the probability density here is 1/2. So I consider two functions, two random variables, one from -1 to 1 to r, and for every omega in this domain, this variable takes the value 1, and x2 takes the value 2 when omega is positive and 0 otherwise. Let me concentrate on the expectation of x2. So x2 will be, because it is 0 for omega negative, so it will be an integral from 0 to 1, because my probability only is defined from -1 to 1. So from 0 to 1 of x2 of omega, which is 2, times the probability, which is 1/2. So 2 times 1/2 cancel out, and then you get that the expectation of x2 is 1. But the x2 can only take the value 2. Okay? So that's why lots of people, they're in certain examples, you are wondering, should I use the expectation? Should I use the maximum of the distribution? Which one is more characteristic of that distribution? So you have to be careful in that context. So this is the uniform distribution that we saw in general. If you have a uniform distribution from A to B, is defined using indicator variables. I emphasize again that indicator variable that you see up there. This is 0 unless you are between A and B. Uniformity implies that this is 1 over B minus A. And all of these results, basically, you can search them on the web, and you can find them in a few minutes, so you don't have to memorize, but you will need to use these results constantly in your calculations. Interestingly enough, and here is, I don't know if it's a paradigm, but or something out of the ordinary, we said that the probabilities have to sum up to 1. That doesn't mean that at a particular problem, particular x, the probability of x cannot be greater than 1. Right? Because at the end of the day, it's the integral that has to be equal to 1, and I can have a delta function as my probability that goes to infinity. All right, it's much higher than 1, so don't, and here's an example actually with a uniform distribution that you can look at. Gaussian distributions basically is the bread and butter of everything in machine learning, and we will do some very weird things with Gaussians, okay? So as much as you think you know Gaussians, you will see that lots of interesting things can come out of it. So the Gaussian distribution, everybody has seen it, looks like that. The mean and the variance, I give you lots of proofs in the notes, starting, for example, with the proof that this is indeed a normalized distribution. All right, so there is a simple calculation that you can read if you are interested. It has two parameters, mu and sigma square, and we will find out later on that from all possible distributions with a given mean and a given variance, the Gaussian has the maximum entropy. It is, so basically has less sort of constraints than any other distribution. Okay, it maximizes the uncertainty beyond the fact that constrains the mean to be mu and the variance to be sigma square, right? So it is a maximum entropy distribution, and this has implications in calculations. I give you proofs that the mean and the variance are indeed what I said they are. Basically, you have to calculate these integrals, and it's good to have this type of calculations handy because they come in different setups. So these are the integrals that you need to be familiar with, and at least for one-dimensional Gaussians. I don't really have much to say on this, so I keep clicking. So the Gaussian distribution obviously is symmetric, so it will not be useful for lots of problems. It has problems. We will see examples when you have outliers in your models, and that has to do with the fact that the tails of the distribution are not fat. So we will like to address that problem. And also the more difficult problem with Gaussians is they have one mode only. So real data basically are having multimodal distributions, multimodality. Of course, we will find out that this is not something that Gaussians cannot help us, because if you use a mixture of Gaussians, all right, you can have multiple modes. Okay, so we will see how to do that. Now, why is the Gaussian the best known distribution? I think everything has to do with the central limit theorem that we will discuss hopefully on Friday, where you will see that when you have the sum of independent random variables, regardless from what distribution they come, they give you Gaussian at the end. And that's the reason why noise, it's always modeled with Gaussians. Okay? At the end of the day, many things, when you sum them up, look Gaussian. Now, I have a few simple examples, and I'm going to finish in 1 minute, that basically, if somebody throws you lots of data and they tell you fit a Gaussian to it, that's a serious problem, right? And the way you do it is you have to estimate what these variables mu and sigma square are. And for those who have seen this before, effectively, you can use what we call the sample mean and the sample variance, and then you can approximate this Gaussian, and it comes out that the sample mean and sample variance are related with what we will learn to be called the maximum likelihood estimate of these variables. So here are some examples, a distribution that doesn't really look a perfect Gaussian, but if you fit this using the sample mean and variance, you get, you fit this histogram like that. If you have something, if you take all these pixels that represent some electromagnetic radiation over many years, you can actually get a perfect normal Gaussian distribution. So the estimates of mu and sigma give you a Gaussian that fits very well with the data. Okay, so I'm going to stop there. On Friday, we have to continue with a few other distributions. Some will be distributions you have not maybe seen before, all right? And we will discuss a little bit about information theory and how information theory and probability come together. Okay, so I'll see you on Friday in the same room at the same time.